Hello again. So we practiced finding hydrogen concentrations when we had a weak acid. Now we find hydroxide concentrations when we have a weak base. To save a little bit of time and to save you a little bit of listening to my voice, I ran through and worked out the base constants for these three in advance. So if you want to crunch those out yourself and confirm that I got them right, that will get us ready to lay into these. Now, the formula, just a reminder, when we were doing acids, our formula was H3O equals root Ka times the acid concentration. Some people write the word acid, some people write Ha as the symbol for the acid, whatever. When you're doing bases, you don't really have to memorize a new formula here. Every one of these things gets replaced with its base counterpart. So instead of H3O, the strongest acid, we get hydroxide, the strongest base. Square root symbol in both of them. Instead of the acid constant, we get the base constant, and instead of the concentration of the acid, we get the concentration of the base. So that's our formula for the rest of these. And what have they told us? They say the SO3's base constant has already been found. It's 1.6 times 10 to the minus 7. And the base concentration is 0.3. So on the calculator, 1.6 times 10 to the 7 negative times 0.3 gives 4.8 times 10 to the minus, what is that, 8. And then square root it, 2.2 times 10 to the minus 4. And that's concentration, so it's in moles per liter. Similar deal for the next one. OH concentration is root. Our base constant is 1.8 times 10 to the minus 5. Sure is nice having that there. And 0.077 is our base concentration. And calculate 1.8 times 10 to the negative 5 times 0.077 equals square root 0.001177, which in scientific notation is 1.2 times 10 to the minus 3 moles per liter. C, methanoate, similar deal. Oh, no, not similar deal, I'm sorry. They tell us the OH concentration in this one, and it's 4.22 times 10 to the minus 7. So our OH is that number they said, 4.22 times 10 to the negative 7 equals root of our base constant, which we know it's 5.6 times 10 to the minus 11 because we worked it out ahead of time, times, I'm just going to use the letter B for the base concentration because it's quicker to write. Okay, we did these same mathematical moves in the acid practice, so how do we get B out of here? We square both sides. And we get 4.22 times 10 to the minus 7 squared. 1.781 times 10 to the minus 13 equals 5.6 times 10 to the minus 11 times B. And then if we want B alone, the trouble is right now it's multiplied by 5.6, so we divide both sides by 5.6 times 10 to the minus 11, obviously. And we get a base concentration of 0.0032 moles per liter, or 3.2 times 10 to the minus 3 if you like. Okay, and like with the acids, sometimes you get a mystery solution and you have to figure out what's going on with it. Here, I'll just put my formula up again. Root KB times base In this case, they tell us our hydroxide concentration is 1.464 times 10 to the minus 5 equals root. We have a mystery solution here, so we don't know what its base constant is. We can't look it up because we don't know which row it is. But we know its concentration, the amount of chemical in there, is 3 moles per liter. So there's our 3. We can solve for the base constant here, and it's similar to what we did in the last one. We square both sides, knowing that will cancel the root, and we get 1.464 times 10 to the minus 5 squared is 2.14 times 10 to the minus 10, and that equals Kb times 3. We want Kb alone. The trouble is it's multiplied by 3, so no problem. Divide both sides by 3. And we get the base constant is 7.144 times 10 to the minus 11. Now, we'd like to look this up in the data book, but the data book is all about acids and doesn't have this. So if we're going to look for a species here, we actually need an acid constant. So there's one more step to do. The acid constant is Kw divided by the base constant. We don't do this very often. It's usually the other way where we know our acid constant and we're trying to find Kb, but this time we're working backwards. So 1 times 10 to the minus 14 divided by the base constant we found gives an acid constant of 1.4 times 10 to the minus 4. And now we can go to our data book and look for acids that have 1.4 times 10 to the minus 4. And the only candidate I see is lactic acid. Hydrogen oxalate is a little too high. So this is consistent with lactic acid. Are we sure it's lactic acid? No, but from the acid constant, it's certainly a candidate. Hope that makes sense. We'll see you next time.